So, mass suspended from a spring and at rest. This is a 2001 paper, question 4. The mass is displaced by 20 millimeters from its rest position as shown. The mass is released and you can see a little graph of displacement against time. So it's a it's a cosine graph. That's the most obvious thing about it. So show by calculation that d squared y by dt squared is equal to minus 158y. So we know that an expression for that, for displacement, will be a cos omega t. The second derivative of displacement we know is acceleration. And if you look in your data booklet, you get this expression. Now remember that omega is not to be confused with angular velocity, it's angular frequency, in other words how fast something is oscillating, and it's equivalent to 2 pi f. So this is negative 2 pi f all squared multiplied by y. So really looking at the frequency of this, you can ascertain that the frequency is 2, because this is really 0.5 seconds. 500 milliseconds is the same as 0.5 seconds, so you have one oscillation in 0.5 seconds, so therefore you have two oscillations in 1 second, so the frequency is 2. So this will be negative 2 pi times 2 all squared multiplied by y. That will give you minus 158. If you multiply that out, minus 158y, which proves the expression that it asks you to do so here. The second part is a bit more difficult. Requires a wee bit of mathematics. As we've already said, the expression for the displacement is y equals a cos omega t. If you see a cosine graph, that's what you're going to write down. If you see a sine graph, you're going to write down y equals a sine omega t. Those equations are in the data booklet. It's just simply selecting the correct one from the shape of the graph. So we know that y is equal to a cos omega t. So if we want velocity from that, all we need to do is differentiate. So it's dy by dt, because we're looking for a graph of velocity and we must put in numerical values, so we're going to have to calculate out something for velocity here. So we need to start off by getting an expression for that. So differentiate that, you get a omega sine omega t, and it's at this point that you're really looking at when you're going to have your maximum value, because from that you can calculate what the shape is going to be like, because you know that it's going to be a sinusoidal shape, so you know that it's going to be shaped like this. If you plot your graph of velocity against time rather than displacement against time, it's going to be sinusoidal in shape. That's what the differentiation tells you, but you don't know what this maximum value is going to be, and that's going to be the same as this minimum value, because it's an oscillation. So what you need to do is to find out when the maximum value is going to occur of dy by dt. So the max value of dy by dt is going to be equal to a times omega. So we're really taking the sine omega t out of the equation, because that's going to give you a really small number. If you put a value for omega in here, this is 2 pi times 2, and then you put a value for time in here. Look at these values, they're in milliseconds, so it's going to be a very small value. So you're going to end up multiplying this a omega squared term by a really small number, so that's going to come out very small. So the maximum value of velocity is going to occur at the amplitude multiplied by the angular frequency there. So that's going to be 20 times 2 pi times 2, which is just basically 2 pi f. That comes out at 80 pi, and if you want that in a number, you'll get 251.2 millimeters per second. So that tells you what the maximum value of v is, and from your knowledge of, this will be in millimeters per second, and this will be in seconds. You know from your knowledge of how simple harmonic motion works, that when a displacement is zero here, that's at its equilibrium position. That's where the velocity is greatest. Remember, it's accelerating through that midpoint and then slowing down. So your graph is going to be sinusoidal in shape. This is going to be 500 milliseconds. Sorry, that's milliseconds there. This will obviously be 0, and then here in the middle that's going to be 250. Then the values here, that's the value that you've just calculated, 251.2. So that's going to be your maximum value up there, and then your minimum value down the bottom. So that kind of holds with this graph. That makes sense, because here at the point where displacement is 0, at 125 milliseconds, the velocity is at its maximum. And the same over here, when it's returned to its equilibrium position in the middle, velocity is at its greatest. So that's how you would construct a graph like that. That should start to make some sense of what the differentiation means. So you're starting off with a cosine graph, making a sine graph. If you were to differentiate again and get a graph for acceleration, it would be a cosine graph again, because you've differentiated again. Part B, a written sort of question. An object has a periodic motion and oscillates between A and B as shown in figure 9. Between points X and Y, the object moves with a constant speed. Explain fully why the motion of the object cannot be described as simple harmonic. Well, that's your key phrase there, is constant speed. You know from looking at the graphs of acceleration in simple harmonic motion, there is an acceleration happening there, so that the speed can't possibly be constant. So what you're really looking to say, well, if you look at your term that we've already got for velocity, it's a omega sine omega t. That shows you that velocity varies with time. So if velocity varies with time, it's not constant. And if it's not constant, then the motion described there is not simple harmonic motion.